In previous lessons, we have seen how to estimate the toggle rate, which can be obtained from simulation of RTL designs, Verilog or VHDL. We have also seen how to look up the dynamic power associated with short circuit currents during switching transitions in a logic gate, as well as leakage power from dot liberty files in our standard cell model. In this final lesson, we will combine all this information and see how we can integrate them to estimate the complete power consumption of switching in a digital circuit. We will cover the method of estimation for individual gates as well as for D flip-flops, and this method is then iteratively applied to every single gate in the synthesized design and every single D flip-flop, and the power consumption of all the individual gates and flip-flops are then summed. We begin by considering the case of a NAND gate with inputs A and B, outputs Y, and the total output capacitance of 20 picofarads. That is 20 picofarads that has been extracted by a post, place and route tool to which has estimated the capacitance from the total length of the wire, the capacitance of all the input gates that are inputs of the gates that are connected to this node, that and as well as the output parasitic diffusion capacitance of this NAND gate. So all of that has been summed into this final figure of 20 picofarads. As further information, the diffusion capacitance of this particular gate, that is an indirect measure of its size, is given as 0.5 picofarads, and we know that the transitions at all the input A and B occur over a time scale of 0.9 nanoseconds. The toggle rate of input B is given as 5 rise and fall transitions, 5 million rise and fall transitions per second, and the net A, the input net A, stays logic high for roughly 60% of the time, whereas for net B, the number of rise and fall transitions is 6 million per second, and the net stays logic high for roughly 55% of the duration of simulation. So the number of output transitions that arise from a toggling of from a transition of net A is given by the toggle rate of Y times the toggle rate of A divided by the sum toggle rate of A and B. Therefore, there are 3.5 million toggles in the output per second that can be attributed to transition in input net A, and there are 4.2 million transitions per second at the output Y that can be attributed to a toggling of the input net B. And we can then estimate the number of toggles in input Y that do not result in a transition at the output. That's given by the total toggle rate of the input minus the toggle rate of the output that is dependent on the toggles of the input. So there are 1.5 million toggles of signal A that do not result in any toggling of signal Y, and on average 1.8 million toggles per second of input B that do not result in any toggling of the output Y. We will now proceed to estimate the dynamic power that is consumed by toggling at the output Y, and this toggling can be associated with mostly the short circuit current that occurs. This is given by the amount of energy consumed by toggles in the output Y that arise from toggling the input A, that is in this line, and the amount of energy consumed by toggles in the output Y that arise from toggling in the output B. This is the energy associated with rising with the energy of toggling the output Y associated with a rise transition in A, and the energy associated with a fall transition in A. Because we are giving the average toggle rate, that is the average rate of rise and fall transitions, we will take the average of the rise and fall energy consumptions. If we know the individual toggle rates of the rise transition and the fall transition, we can actually just directly sum them up here without having to take the average. Okay, and so the units of energy here, because we had picofarad units in capacitance and volts units of voltage, so the units of energy can be computed as in picojoules. So we can now sum the contribution of transitions due to input A, that is 12.3 nanowatts, and the contributions of transitions due to input B, that is 10.68 nanowatts, and the total dynamic power associated with the switching activity internally, that is from the short circuit current, is estimated to be 23.02 nanowatts for this particular NAND gate with this particular transition times, and with a size given by the output capacitance and transition time of 0.9 nanoseconds. We also need to estimate the energy and power that is consumed for charging the external load at the output here, and this is given by half C VDD squared times the toggle rate of the output Y. Okay, and in this case I had, for illustrative purposes, I've used a 1.1 volt supply, so 0.5 times 2.20 picofarad times 1.1 volt squared times 7.7 mega toggles per second gives rise to 93.17 microwatts for the output charging power. So the total active power, or the total dynamic power, is 23.02 nanowatts plus 93.17 microwatts, and this is going to be approximately equals to 93.17 microwatts. So for this particular NAND gate, because of the large output capacitance, the energy consumption is dominated by the output charging power. And we can just simply look up the total leakage power of this particular NAND gate from the .liberty file. Now let us see how we should compute power consumption from flip-flops. Here we have a D flip-flop, and it is given that rise and fall transitions at the input occur with a 0.24 nanoseconds rise time. Okay, and this input has a toggle rate of 25 mega toggles per second, and it remains logic high at roughly 60% of the time. And the clock, it has a toggle rate of 500 mega transitions per second. So this is 500 mega transitions per second with a 50% duty cycle. And here the rise transition is very short, occurring only in 0.06 nanoseconds, while the fall transition occurs at a longer time duration. And this is the static switching activity probability and the toggle rate at the output of the flip-flop. And we understand that it's given that the output capacitance, that is Q, and this refers to the size of the flip-flop, is given as 0.5 picofarad, and the transition time at this output is given as 0.24. Transition time at the input is given as 0.24 nanoseconds. and the load sitting on this, which is the wire capacitance plus the total input capacitance of all the gates that are connected to this, the output of this flip-flop, is given as 20 picofarads. The internal power consumed, that is the dynamic power associated with short circuit currents and switching activity, is simply the sum of the power incurred by transitions at the input D, transitions at the clock input, and transitions at the output Q that have arisen from transitions at the input D. Okay, and similar to the estimates of gate, we can look up the rise and fall energies. And this, in this case, because we do not differentiate between the toggle rates of rise and fall times, we just take the average of rise and fall energies to compute the total power consumed by dynamic activity, that the dynamic power arising from switching, and this is attributed to the short circuit current. And we can repeat this for the output Q as well as the clock, and we sum them out to get the total internal switching power for the D flip-flop. The output charging power, that is the power to charge, the energy consumed and the power delivered to charge the output load capacitance here, is also half C VDD squared times the toggle rate. We get this value, and the total active power is the sum of the internal dynamic power, that is power associated with short circuit current, and the output charging power here given as follows. So I think this unit is also in microwatts. And the total leakage power can simply be looked up from the D flip-flop Liberty file. So let's take a look at the D flip-flop Liberty file. We see that the leakage power is just given as an average value and not a conditional value. And we have associated with the input pin here the capacitance, average capacitance, rise capacitance, fall capacitance, and this specifies that this input pin is actually a clock. And internal switching power, that is power associated with the short circuit current, can be consumed by clock transitions, and this power here, specified here, is consumed irrespective of what happens at the output. This is consumed at the input itself. Okay, just because the input clock is switching, and the index here refers to the transition time, that is the time it takes to transition, to make a rise transition or fall transition. And we will remember we were given that the transition is actually 0.24 nanoseconds. So this is where you would read the dynamic power associated with clock rise transitions and the dynamic power associated with clock fall transitions. This is similar for the input pin D. You have rise and fall capacitance, as well as rise and fall power associated only with switching at the inputs. And here we see the definitions for the output of the flip-flop Q, and that is given as rise and fall powers, that is rise power and fall power consumed when the output Q switches in response to activity on the clock. Okay. And this is dependent on the size of the flip-flop given by the output capacitance 0.5, that gives us the second row of the table, and the rise transition time of 0.24 nanosecond, that is the input transitions have a rise time of 0.24 nanoseconds and a fall time of for the clock the rise time is 0.06, so we should be looking at this value, and for the fall time is 0.24, we should be looking at this value. Now, to conclude this lesson, although the method of specifying a table of energy values consumed during the dynamic switching is a common method, and if you were to size the gate of flip-flop at an output capacitance that is somewhere in between what has been specified here, you would simply perform an interpolation between the table values. There are more advanced methods which give you more level of details that can be applied to simulations, and these advanced methods of specifying uh, dynamic dynamic power and leakage power typically specify it through composite current sources. That is, the current values themselves are specified as a function of um, capacitance, rise time and rise time, and input transition time, and the time during which the current is applied. Okay, as an example, the leakage current rather than the leakage power can be specified here, and here this is actually specifying a conditional leakage current when A1 is logic 1 and A2 is logic 0 and Zn is logic 1. This is the condition of the two input gates, and the leakage current arising coming from the VDD is given as 6 to the power minus 6 to the power of 6 times 10 to the power of minus 6 microamps. Remember the units. And the current leakage associated with VSS is 4 times 10 to the power minus 6 microamps. So this is actually 4 picoamps. And the leakage power associated with the gate, that is from the gate to the bulk, is given as these numbers. Okay. The currents can also be specified for switching activity, that is the short circuit currents associated with switching of the with a transition at the output given transitions at the input. So this is the switching that arises from inputs A and the outputs Zn. And the condition where we define these currents are on a fall transition at input A and a rise transition on output Zn. We can specify the currents coming out being drawn from VDD as the following values. Oops, sorry. As the following values. Let's go back. As the following values given in this table, corresponding to a specific input transition time, that is the transition time for AN making a fall transition, an output capacitance of 0.9 picofarads, and a time value here associated with the time of the input crossing the threshold.